Hello students, hope all of you are doing good. I'm Dr. Seema Singh and you're watching my channel Bonding with Chemistry. Today we'll continue with part 5 of chapter 3 Metals and Non-Metals. Until now we have covered what are metals and non-metals as well as their physical properties. We've also learned about metallic bonding, which is responsible for the physical properties exhibited by metals. Today I'll take up the first part of a 5-part series on chemical properties of metals. I've intentionally divided this topic into 5 subparts. This is because this topic involves plenty of chemical equations. Now students, chemical equations have not only to be understood but thereafter memorized, and this process requires a great amount of written practice as well as your time. Therefore, fragmenting up bigger topics will not only help you to channelize your entire energy to understand a small topic in one go or one sitting, but will also give you a sense of accomplishment towards the end of this video. In my next video, I'll take up reaction of metals with water. Therefore, for receiving latest updates, kindly spare a moment and do please subscribe to my channel and also hit the bell icon. To begin with, let me give you a brief about all the chemical properties of metals that are in your current syllabus. We are going to study the reaction of metals with oxygen in today's video. Thereafter, we will learn what happens when metals react with water, followed by reaction of metals with acids and reaction of metals with solution of other metal salts. Finally, we'll also learn about reaction of metals with non-metals. Before we begin with the first property, it is very important that we understand the need for studying chemical properties. In our previous videos, we learned that metals and non-metals can be differentiated on the basis of their physical properties. But is that enough or sufficient for discriminating the two? No, because there are quite a few exceptions. For instance, we say metals are hard, whereas non-metals are soft. But metals such as lithium, sodium, and potassium are so soft that they can be easily cut with a knife. Whereas diamond, an allotrope of carbon, which is a non-metal, is the hardest known natural substance. Similarly, metals are said to possess high melting point and boiling point. But metals such as gallium and cesium can melt by the heat provided by our pumps. On the other hand, non-metals are said to possess low melting point and boiling point. But graphite and diamond have very high melting points. Similarly, there are many other exceptions about which we have already learnt in my previous videos. Thus, we see that physical properties cannot be the sole criteria for differentiating metals and non-metals, and hence the need for studying chemical properties of metals and non-metals. Let us undertake an activity to understand how chemical properties help us in identifying or differentiating a metal and a non-metal. I'm sure you are familiar with the first part of the activity, which is burning off a magnesium ribbon in air. In fact, this was the first activity that you studied in this class in Chapter 1, Chemical Reactions and Equations. The link is provided on top for you to refer. For this activity, we will take a small strip of magnesium, clean it with a sandpaper so as to remove the oxide layer that might have formed on its surface when the metal magnesium comes in contact with atmospheric oxygen. Thereafter, holding it with a pair of tongs, we'll burn this ribbon in the flame of a Bunsen burner. The white powder that is formed on burning is collected in a watch glass or a china dish and subsequently dissolved in water by stirring. The resultant solution is tested with red and blue litmus papers. You can also take litmus solutions. Similarly, we take a non-metal, say sulphur powder, which is yellow in color, in a spatula and burn it in the flame of a Bunsen burner. We observe that the sulphur melts and then converts into vapors. We collect the vapors or the fumes evolved in a test tube that is kept inverted over the burning sulphur that we took in a spatula. Thereafter, we add a little amount of water in the test tube containing fumes and test the resulting solution with red and blue litmus papers. Now let us discuss the observations and inferences that we draw from these activities. In the first case, that is burning of magnesium ribbon in air, we observe that the magnesium ribbon burns with a dazzling white flame or brilliant light. On testing the solution, we observe that it changes red litmus blue, but the blue litmus remains unaffected. This shows that the solution is basic or alkaline in nature. The equation involved in these reactions are: magnesium burns in oxygen to give rise to white color solid magnesium oxide. When this magnesium oxide is dissolved in water, it gives rise to magnesium hydroxide, which being basic turns red litmus blue. Thus we infer that magnesium burns in air to form magnesium oxide, which is a basic oxide. Coming to the observations of burning of sulphur. Sulphur burns in oxygen to produce sulphur dioxide gas, which has a pungent suffocating smell. You can see the equation here. S, when burns in oxygen, it gives rise to sulphur dioxide. Now this is the pungent gas. When the fumes of sulphur dioxide gas are dissolved in water, you get sulfurous acid. Look at the formula, it is H2SO3. It is not H2SO4. Your H2SO4 is sulfuric acid, and this is known as sulfurous acid. And what do acids do? Acids turn blue litmus red, whereas they have no effect on red litmus. Thus, we can use this activity to differentiate metals and nonmetals on the basis of their reaction with oxygen. Metals react with oxygen to give rise to metallic oxides, which are generally basic in nature, whereas nonmetals react with oxygen to give rise to nonmetallic oxide, which are generally acidic in nature. My dear students, you will learn sometime later in this video itself that few metal oxides are amphoteric in nature. We will learn what this word means a little later. Let us focus on chemical properties of only metals now. We have learned that there are around 95 metals in the periodic table. In my video on metallic bonding, we also learned that in terms of electrons, metals are chemical elements that have tendency to lose one or more electrons present in their valence shells to form positively charged ions. Metals are therefore regarded as electropositive elements. After losing the valence electron, they achieve the electronic configuration of the nearest noble gas element. For example, sodium, which has electronic configuration of 281, loses one valence electron to form sodium ion, which has electronic configuration 28, which is similar to that of the nearest noble gas electronic configuration, which is neon, having atomic number 10 and configuration 28. Well, this tendency of losing electrons varies from metals to metals. Some metals have tendency to lose electrons easily, whereas the same process is slightly difficult for others and extremely difficult for some. Due to this, the reactivities of metals towards a chemical substance also differs, and they are thus ranked on the basis of their reactivities. If you give a thought, this ranking has become a crucial aspect in all fields. We rank players on the basis of their performances or scores, businessmen top 10 on the basis of their fortune, chefs on the basis of their cooking, etc. In every profession, you have the top 10 criteria. Let me give you an unfortunately sad but a true and more relatable example of this ranking system. You might have witnessed the same thing happening so often in a classroom. A teacher teaches a topic to a class full of students. Some students will be quick to grasp the concept taught. Some might take a little time to understand. Maybe the teacher needs to repeat. And quite a few might be unable to understand the concept at all, even if the teacher repeats or changes the method of his or her explanation. So, the level of understanding of each student is different. That is, we have the same teacher teaching the same concept, but the way each student responds to her teaching differs. And if on the basis of this understanding, a teacher has to categorize the students, the category might be quick learners, average learners, and slow learners. But remember, they are all learners with unique characteristic and importance. Our metals have also been unable to escape this ranking system. Based on a metal's reactivity, scientists have categorized them into most reactive metal, least reactive metal, or active metals, inactive metals, and noble metals. A list of metals arranged in the order of decreasing reactivities is known as reactivity series or activity series. Remember, we had studied this series in Chapter 1 Chemical Reactions and Equations under the topic Displacement Reactions. My dear students, note that this reactivity series contain plenty of other metals, but we will restrict our list to only those metals which we require for our current syllabus or current class level. So here is that list. Now there are plenty of mnemonics with the help of which you can remember this series. The one that I have created goes like, please stop calling me a zombie. Instead, let her call me sleeping genius. Another mnemonic I had discussed in my video on displacement reaction, whose link is provided on the top for you to refer. There are several other famous mnemonics available on internet in English as well as in Hindi, such as please send Charlie's monkeys and zebra in lead hardened cages securely guarded, or please send cats, monkeys and zebras into lovely hot countries, signed giraffe. You can choose the one you like or create your own. In case you create your own, do remember to share in the comment section below. In the reactivity series, hydrogen, despite being a non-metal, is included because it helps to compare the reactivities of the metals. We will learn in subsequent videos that the metals which are placed above hydrogen in the series, being more reactive, can displace hydrogen from acids such as hydrochloric acid and sulfuric acid. Thus, hydrogen acts as a basis of comparison. Now, as you can see in this reactivity series, the most reactive element is placed at the top and the least reactive element at the bottom. If you will look at the complete list of metals in the reactivity series, you will find that platinum is the least reactive metal. It is not gold, but platinum. But since we do not require platinum for our current study, we are going to stick with gold, the least reactive metal. More reactive metals such as sodium, potassium, etc. have a greater tendency to lose electrons and form positive ions as compared to metals at the bottom of the series. This reactivity series has been developed after performing a series of reactions or experiments such as single displacement reaction, reaction of metals with water, acid, etc. So if we know the series, we can predict the various reaction of metals such as these. As we will study different chemical reactions of metals in this and subsequent videos, we'll keep this list handy for use. In fact, I would suggest pause this video for some time and try to memorize this series. Coming to the first chemical properties of metals, that is the reaction of metals with oxygen. In this property, we will study the following. Number 1, the reaction of different metals with oxygen. 2, the nature of the metallic oxides formed. And finally, the solubility of metallic oxides in water. We have already witnessed in the beginning of this video how the metal magnesium reacts with oxygen. To further understand this property, let us repeat the same activity with few more metal samples such as aluminium, copper, iron, lead, zinc and sodium. We have already studied with magnesium. You can easily find these samples in your science laboratory. My dear students, make sure you perform this activity only in the presence of your teacher. Hold each metal sample with a pair of tongs and try to burn them over the flame of a Bunsen burner and collect the product formed in each case. Let the products as well as the metal surface cool down. Thereafter, make the following observations. Which metals burn easily? Next, what was the color of flame when the metal burned? How does the metal surface appear after burning? Are the products of the reaction soluble in water? And finally, arrange the metals in decreasing order of their reactivity towards oxygen. We will try to find answers to all these questions slowly in this video. First of all, let us understand what happens to metals when they burn or react with oxygen. Metals combine with oxygen to form metal oxides. Now, the general equation for the reaction of metals with oxygen can be written as metal, which is solid in nature, combines with oxygen, which is gaseous in nature, to give rise to metal oxide, which is again solid in nature. For example, magnesium combines with oxygen to give rise to white color solid known as magnesium oxide. Aluminium combines with oxygen to form aluminium oxide. Similarly, almost all metals combine with oxygen to form metal oxides. When I say almost all metals, it means majority of them. Few metals such as gold and silver do not react with oxygen at all. They are said to be exceptions. The metal samples we took, or metals in general, do not react with oxygen with same ease. Some react with oxygen vigorously even at room temperature, some of them on being heated, few others on being strongly heated, some on prolonged strong heating, and a very few like gold, silver, and platinum not at all. Depending on this, we'll try to make an attempt to arrange the metal samples in decreasing order of their reactivity towards oxygen. Also note that most of the metal samples which we have taken give characteristic color to the flame of Bunsen burner. Let us study each metal sample in detail, beginning with sodium metal. You will observe that sodium reacts vigorously when heated in air. It imparts an intense yellow color to the flame or burns with a bright yellow color. Since lot of heat energy is evolved, the metal can catch fire and the reaction might become explosive. So be very cautious while carrying out this reaction and do it only under the supervision of your teacher. In fact, you need not even heat sodium metal as it can react itself with the oxygen present in air at room temperature. Therefore, to cut off its contact with oxygen as well as moisture, sodium is kept immersed in kerosene oil. We discussed this part in one of my previous videos. The same is true for potassium metal. It too reacts vigorously in air to form potassium oxide. Potassium imparts a lilac or light purple color to the flame. You can see the chemical equations for both the reactions here. So based on their reactivity, we can place both sodium and potassium on top of the reactivity list as the two most reactive metals. Next we have metals such as magnesium, aluminium and zinc, which do not react with oxygen at room temperature just like your sodium and potassium did. But on being heated, they burn to give rise to their respective oxide according to the following equations. Magnesium on being heated burns in air with a dazzling white light. Remember, Magnesium metal burns with a dazzling white light. It does not impart color to the flame. It simply burns with bright light, just like the light emitted if you burn a sparkle on Diwali, Fulchari. Aluminium imparts a silvery white color to the flame on being heated and give rise to aluminium oxide. Zinc, just like magnesium, does not impart any color to the flame and combines with oxygen to form zinc oxide. All these reactions are not as vigorous as those of sodium and potassium. Therefore, we place these metals second in our list of reactivity. The next metals to rank or rate are iron, lead, and copper. All these metals do not burn in air at room temperature or on heating, but on prolonged heating. What do we mean by prolonged heating? It means heating the metal for a long time. They react with oxygen to form respective oxides. Students note that although iron metal in the form of rod does not burn, but iron filings, small pieces of iron that look like powder, when sprinkled on the flame of Bunsen burner, burn vigorously with golden orange or orangish brown color. This happens because the surface area of iron filings is greater than that of an iron rod. Similarly, finely divided lead powder is pyrophoric in nature. By pyrophoric, we mean it is a fire risk. Copper on prolonged heating turns red hot first and then reacts with oxygen to form a black coating of copper 2 oxide, also known as cupric oxide. Why? Because the oxidation state or valency of copper here is +2. Had it been +1, it would be called as cuprous oxide. The equations involved in the above reactions are provided here. Learners note that Fe3O4, which is formed when iron combines with oxygen, is a mixture of iron 2 and iron 3 oxide. That is, it is a mixture of FeO and Fe2O3. Here the oxidation state or valency of iron is +2 and here it is +3, and therefore we write iron 2,3 oxide as the name of the product, which is more accurately written as ferroso-ferric oxide. This you're going to study in your higher classes. Even if you write iron 2,3 oxide, it is absolutely correct. These are the colors which these metals impart to the flame of the Bunsen burner. Students also note that you might not find some of these reactions in your NCERT textbook, but since an activity involving these metals and their reaction with oxygen is prescribed in your syllabus, you need to know them. From these reactions, we can conclude that copper is less reactive than both iron and lead, and thus our reactivity order looks like this. Looking at this list, we can say that sodium and potassium belong to the category of most reactive metals and copper the least reactive. We see that all these metals react with oxygen, though the rate at which they react and the reaction condition varies. As already stated, there are few metals such as gold and silver that do not react with oxygen at all, not even after prolonged strong heating. That means no matter how much you heat them, they will not react with oxygen at all. These metals are known as noble metals and are the least reactive ones. Let me add these metals to the list of metals that we took for the activity. So I'm going to place here gold and silver. Obviously, you will not find these metals in your chemistry labs. They are pretty expensive. Hypothetically, we are going to place them in the list. And therefore, we can say gold and silver will occupy the last slot of the reactivity order, the least reactive metals. So, the order of decreasing reactivity finally becomes like this. But as you can see here, there are few metals that occupy the same slot. For instance, sodium and potassium both belong to number 1. Magnesium, aluminium, zinc occupy the second slot. The third slot is occupied by iron and lead. Then we have the fifth slot occupied by gold and silver. Now you can't have tie positions. You need to provide a tiebreaker. Thus we say reaction of these metals with oxygen does not help in clearly deciding the reactivity order. We have to give a tiebreaker. We have to perform more experiments or reactions to help us decide the reactivity order of metals as provided in the reactivity series. We'll study about those reactions in subsequent videos. Coming back to this activity, let us address the remaining questions of observations about the nature of metallic oxides when metal react with oxygen and their solubility in water. After collecting the oxides of respective metals in a watch glass or test tube, we added a small amount of water and tried dissolving them. We observe that oxides of metals such as sodium and potassium dissolve in water to form soluble hydroxides. The corresponding chemical equations are Na2O dissolves in water to form sodium hydroxide and K2O, that is potassium oxide, dissolves in water to form potassium hydroxide. When we test these hydroxides with both red litmus and blue litmus paper, we find that they turn red litmus blue but have no effect on blue litmus paper. Thus, metal oxides are basic in nature because they react with water to form bases. Since the hydroxide formed are soluble in water, we call these bases as alkalis. Only few metal oxides such as sodium oxide and potassium oxide are soluble in water. Most of them are insoluble in water, and thus the corresponding hydroxides remain as suspension. For example, hydroxides of aluminium, zinc, iron, copper are insoluble in water. They form suspension. Magnesium hydroxide, known as milk of magnesia, is insoluble or slightly soluble in water and remains suspended. All these metal hydroxide turn red litmus blue and thus are known as bases. Since hydroxide of these metals are insoluble in water, we cannot call them as alkalis. They are simply called as bases. Thus, water-soluble bases or metal hydroxide are termed as alkalis and water-insoluble metal hydroxides are simply called as bases. Now we can make a general statement. All alkalis are bases, but all bases are not alkalis. Take a moment and think about it. Well, as these metal oxides are basic in nature, they react with dilute acids to form salts and water. We can recall from one of our earlier videos on neutralization reaction. I've provided the link on top for you to refer. In neutralization reaction, an acid is neutralized by a base and vice versa to give corresponding salt and water as products. Some examples of metal oxides reacting with dilute acids are reaction of black color copper oxide with dilute hydrochloric acid to give blue-green colored copper chloride or cupric chloride. Similarly, white color magnesium oxide reacts with dilute sulfuric acid to give rise to magnesium sulfate salt and water as products. Dear students, note that although most of the metal oxides are basic in nature, some metal oxides such as aluminium oxide and zinc oxide show both basic as well as acidic character. Therefore, they can react with acids as well as bases. Such metal oxides are known as amphoteric oxides. Students, this definition along with examples in the form of chemical equations is asked quite a few times in your examination, both internal and boards. So kindly make a good note of it and mark this topic as a very important topic. These are the chemical equations illustrating the amphoteric nature of aluminium oxide and zinc oxide. You can see here aluminium oxide reacts with an acid, so here it is going to act like a base. In this equation, it is going to act like an acid reacting with the base to give rise to sodium aluminate. This is an important reaction, and remember to balance the chemical equation. Zinc oxide reacts with acid, so this equation shows its basic character, whereas this one shows its acidic character. And here you have sodium zincate plus water as the products. Another important point is that at ordinary temperature, the surfaces of metals such as magnesium, aluminium, zinc, lead, etc. get coated with a protective oxide layer. This is because these metals are quite reactive. They react with atmospheric oxygen and form the corresponding oxide layer. It is called as a protective covering or layer because it prevents the metals from further oxidation, making them passive. Here, passive means that which is not active or that which is not reactive. And because of this, we rub the metal surface with the sandpaper before heating them in air. This is done to scrub off the protective oxide coating. We have studied this part quite a few times in our previous videos. This feature or property of these metals, especially aluminium, can be further enhanced artificially and put to good use. Let us understand how. Aluminium is known as a self-protecting metal because of its tendency to form a thin coating of aluminium oxide when it comes in contact with atmospheric oxygen. That means if this is a metal aluminium, when it comes in contact with atmospheric oxygen, it develops a protective coating of Al2O3. This coating protects aluminium from undergoing corrosion. We have studied what is corrosion in chapter 1. If need be, you can refer to the link provided on the top. This resistance of aluminium from corrosion can be further improved by making the oxide layer thicker. And this process of forming a thick oxide layer on the surface of a metal artificially is known as anodizing. Anodizing can be achieved by the process of electrolysis. Remember, we studied electrolysis of water in chapter 1, decomposition reaction. If in case you need to brush up, you know where to find the link. For anodizing, we take an electrolytic cell in which aluminium metal acts as an anode, that means the positive electrode. Dilute sulfuric acid is the electrolyte used. When electric current is passed, oxygen is evolved at the anode. So this is your anode. Oxygen is going to be evolved here. This oxygen combines with aluminium to form aluminium oxide. And this aluminium oxide gets coated on the surface of the metal. We can control the thickness of this coating by adjusting the quantity of charge that is passed. Don't worry students, you don't have to get into details of this process at this level. Just try and understand briefly what is anodizing only for your information. The coating that you get after anodizing is quite hard and resistant to attack of airs, chemicals, etc. You must have seen anodized aluminum cookwares or the window and door frames. In fact, this oxide layer can be colored or dyed easily to give aluminium articles an attractive finish. You must have seen or used carabiners, the connecting hooks, which are widely used in rope-intensive activities such as mountaineering, climbing, window cleaning, and acrobatics, etc. They have an anodized aluminium surface which are dyed with different colors. Here you can see golden orange, blue, green, etc. Well, why is this process called as anodizing? This is because the part that is being treated, here that part is aluminium rod. That part forms the anode or the positive electrode of an electrolytic cell, and hence the process is known as anodizing. With this, we complete the first chemical property of metals, that is their reaction with oxygen. I will wind up this video with an NCERT exercise question which says, Pratyush took sulphur powder on a spatula and heated it. You can see here, this is sulphur powder, it's being heated. He collected the gas evolved by inverting a test tube over it, as shown in this figure. What will be the action of gas on number 1, dry litmus paper. Number 2, moist litmus paper. We have also to write a balanced chemical equation for the reaction taking place. So let us begin with writing a reaction first so that we know which gas has been evolved. So we have sulfur powder. It combines with oxygen to give rise to sulfur dioxide gas. Next, we need to find out what will be the effect of sulfur dioxide on dry litmus paper. Now, if you recall what we studied in chapter 2, acid, bases and salts, about acids and bases, we've read that acids are going to furnish H positive ions and bases OH negative ions only in presence of water. This is a dry litmus paper. It has no moisture or no water, and therefore SO2 will have no effect or will show no effect on dry litmus paper, whether the litmus paper is red or blue. Now, if we take moist litmus paper, that means this sulfur dioxide is going to react with the moisture present in litmus paper, that is water, to give rise to H2SO3, sulfurous acid. We've already covered this in today's video in the explanation part. Now, this is sulfurous acid. So, what do acid do to red litmus paper? It shows no effect. And what it will do to a blue litmus paper? It will turn blue litmus red. The next part is write a balanced chemical equation for the reaction taking place. So we've already done this part. These are the two reactions. Even if you write the first reaction, you get full marks because they've asked for the reaction taking place. They did not say reactions. But in my opinion or my suggestion, you should mention both the reactions because only then you'll be able to find out what will happen when you treat the gas with moist litmus paper. So your answer, if you want to check, the gas SO2 will have no effect on dry litmus paper. It will turn moist blue litmus paper red and will have no effect on red litmus paper. S plus O2 give rise to SO2 is a already balanced chemical equation. If you want, you can give the second one. SO2 reacts with water to form sulfurous acid, and because of the formation of this acid, moist blue litmus paper turns red. With this question, I come to the end of this video. If you like my video, do please spare a moment and give it a thumbs up. In my next video, I'll take up the next chemical properties of metal, that is the reaction with water. So stay tuned to my channel, please subscribe to it and share this video with anyone who you feel might benefit. Thanks for watching, and until next time, take care and stay bonded, my dear learners.